Albert Einstein dreamt of finding a unified field theory, a single equation that might account for every fundamental process in nature, from the jostling of atoms to the wheeling of the galaxies. Today, science is close to fulfilling Einstein's dream. The nucleus of the atom has yielded up evidence of an elegant simplicity underlying the wild diversity of the universe. New unified theories are being written that reveal traces of this primordial simplicity. The 1984 Nobel Prize in Physics was awarded for experiments that confirmed the first of these new theories. Experiment and theory alike indicate that the universe began in a state of perfect simplicity, evidence of which was burned into the heart of every atom in the heat of the Big Bang at the beginning of time.
We have a pretty good understanding of the history of the universe from 1/100th of a second after the Big Bang until today, 15 billion years later. And it's pretty remarkable that I can say this, and it's even more remarkable I can say it and the men in white coats don't come and pull me off the stage. And I think that part of the history we have pretty much nailed down, because there are fossils and relics that are left behind that tell us that our theory is right.
Cosmology, it turns out, provides, in a way, a sort of testing ground for some of the ideas of elementary particle physics. We can't observe the early universe, but we can observe its consequences in the universe of today. What's it like out there?
I don't know what it's like out there. It's cold, it's impersonal, it is the machine, if you like to put it that way, that has created you. Now, by that I mean the following. Every single atom in your body was once inside a star. We are all brothers in that sense.
To know the atom, it seems that we must know the universe. And to know the universe, we must know the atom. In a confluence of large and small that would have gladdened Einstein's heart, the search for simplicity is bringing science face to face with the ancient enigma of creation.
When I was a boy, I used to bring a telescope down to the shore, point it up into the sky, and look out into what I took to be the universe. I had read in the astronomy books that what we see in the sky is the past. The Big Dipper, for instance, is a star cluster 75 light years away. That means it takes light from the stars of the Big Dipper 75 years to speed through space and reach our solar system. If you're lucky enough to get to be 75 years old, you can see the Big Dipper just as it looked on the day you were born. This star cluster is further out. It's in the constellation Hercules, and it's 27,000 light years away. That means that we see it as it looked 27,000 years ago, back when horses stood only half a meter high, there wasn't a human city anywhere on the face of the earth, and the great whales were new to our world. One way to study the history of the universe is to look out into deep space. But the universe, after all, isn't all out among the stars and galaxies. It's also right here at home. We live in the universe. And ordinary objects are full of clues to cosmic history. Every stone on the beach is a galaxy of atoms, and those atoms have a history that goes back longer than the history of the Earth. Before the Earth was formed, those atoms were adrift in interstellar space. Before that, some of them were incorporated into ancient stars. The subatomic particles that make up these atoms can trace their lineage back 15 billion years to the beginning of time. In this program, we'll explore the history and the origin of the universe. we'll look down into the minuscule world of the subatomic particles and out toward the cosmological frontiers of space and time. Our hope is to learn something about how everything got to be the way it is. Clues to that riddle are all around us.
Skyscrapers cluster in the Wall Street district of downtown Manhattan. For more than a mile to the north, there are no tall buildings. And then, in Midtown Manhattan, the skyscrapers sprout up again. It's a natural development, its destiny laid down hundreds of millions of years ago when molten lava flowed through the Hudson River Valley. The bedrock on which the city is built was crumpled and wrinkled by geological processes, and the result was a pair of underground mountains. Since skyscrapers must be rooted in bedrock, the swayback form of the Manhattan skyline traces out the contours of a subterranean mountain range. It's here that we begin our exploration of the realm of the atom and the depths of the past.
Times Square is about as unnatural a piece of real estate as you can imagine. And yet it, too, has been shaped to a considerable extent by its natural history. The planetary processes that shaped it are, by and large, too imperceptibly slow for us to notice on the human time scale. But imagine that we could walk into the past at an accelerated rate. Then we could see how the geology of Times Square was shaped. Let's try it. Let's walk into the past at the rate of a century per step.
A century ago, Times Square, known then as Longacre Square, was a dark, dangerous place, a haven for muggers. Its transformation into the Great White Way, a brighter if not substantially safer place, was due to the applied physics of Thomas Edison and his invention, the electric light. 200 years before that, Times Square was farmland. The Hopper family raised cabbages at Broadway and 50th Street. A few more steps into the past, and Broadway was an Indian trail. Only 70 steps, 7,000 years ago, and Manhattan has yet to be discovered by the Indians. A little over 100 steps, and we've come to the epoch of the mastodons. This was one of the mastodons' favorite grazing grounds. We today call it Central Park.
Only 150 paces suffices to take us back to the most recent ice age, when Manhattan was buried under a sheath of ice over 1,000 feet thick. This boulder is what the geologists call a glacial erratic. It was pushed down here from upstate by the advancing ice. And you can still see how these exposed rocks were polished by the glacier as it moved south. But the rocks themselves are millions of years old. To walk that far back in time at a century a step, you'd have to walk to the North Pole, and the Earth is billions of years old. To go that far, you'd have to walk clear around the world. Scientists deal with big numbers like these by using what they call exponentials. For instance, powers of 10. 10 to the second is 10 times 10, or 100. 10 to the third is 10 times that, or 1,000. This time, let's imagine that we can walk deeply into the past exponentially by letting each step count for 10 times as much as the step that preceded it.
A month ago, a year ago, 10 years ago, 100 years ago, 10 to the third, 1,000 years ago, and the city vanishes. 10,000 years ago, Manhattan was still awash with the melt of the ice ages. For 1 million years before that, the glaciers advanced and retreated, cutting great furrows that filled with runoff water. One of them became the Hudson River. $100 million years ago, Manhattan lay at the floor of the Cretaceous Sea. Prior to that, North America was still connected to Africa. Volcanoes spewed forth lava in which the skyscrapers of Manhattan were one day to take root. 1 billion years ago, New York City was the site of a mountain range as imposing as the Alps. Four to 5 billion years ago, the Earth was still condensing from fragments of rock circling the sun. Before that, there was no Earth, just a drifting interstellar cloud from which the sun and its planets were to form. Tennyson wrote of the abyss of time, "O Earth, what changes hast thou seen? There where the long street roars hath been the stillness of the central sea. The hills are shadows, and they flow from form to form, and nothing stands. They melt like mist, the solid lands. Like clouds, they shape themselves and go."
The Earth is old, but older still are the atoms that compose the earth and the air, you and me and this tree. And we can investigate the depths of cosmic history by looking at nature on the atomic and the subatomic scale.
The more closely we scrutinize the universe of the very small, the more evidence we find there of the past. The pollen blossoms caught in this tree are young, but their color and form were generated by genes that are older than the plant itself. The genes, in turn, are built upon DNA molecules. The molecules become visible at a magnification of 10 million times. Each is a library of genetic information accumulated over eons in the evolution of life. Moving in more closely still, we can see the carbon atoms of which the DNA molecules are made. They're even older than the Earth. The outer precincts of the atom are patrolled by a shell of negatively charged particles, the electrons. Photons carry electromagnetic force between the electron shells. We pass through the inner shell of the carbon atom. We're approaching one of the oldest and most magnificent structures in nature, the nucleus of the atom. The nucleus is made of protons, here colored orange to indicate their positive electrical charge, and electrically neutral particles, the neutrons. And these nuclear particles are in turn made of trios of even older and more fundamental particles, the quarks. We've reached the realm of the nuclear forces. The weak force mediates the process of radioactive decay, while the strong force binds the quarks together, weaving webs of energy into the forms we call matter.
Most of what we know about subatomic particles has been learned by accelerating the particles to a high velocity, colliding them with one another, and studying the debris that comes flying out. One physicist compared it to smashing a pair of elegant Swiss watches together and then trying to figure out how they were designed by looking at the cogwheels and screws that would come flying away. It's not the world's most elegant or subtle method, but it works.
This was the world's first particle accelerator. It employed principles that are still in use today. Positively charged nuclear particles, protons, were injected into this little ring, where they were subjected to a powerful electromagnetic field. Since protons are positively charged, they were pulled around toward the negative side of the field. Then the polarity of the electrical field was reversed, hurrying the protons around here, and by repeating the process, you could get them going at a pretty good clip until they spiraled on out to the edge of the ring and finally collided with this target here. This prototype was built in Berkeley, California in 1930. It won its inventors a grant of $500. They used the money to build a second accelerator, twice its size. That one was followed by another, still larger accelerator. Particle accelerators have been getting bigger and bigger ever since. The larger the accelerator, the smaller the scale to which it can probe the fundamental structures of nature. And I'm standing in the midst of one of the world's largest particle accelerators. It's Fermilab on the Illinois plains. It works much like the first accelerator, by using electromagnetic force to whirl particles around a ring. But the ring has gotten larger. At Fermilab, it's 3 miles in circumference. In a tunnel smaller than a fire hose buried beneath the Earth, particles are accelerated to nearly the speed of light and then collided with a fixed target. The resulting explosions, recorded in detector tracings like this one, reveal a wide variety of subatomic particles that interact by means of 4 fundamental forces: gravitation, electromagnetism, and the weak and strong nuclear forces. The way physics sees it, particles and forces are the authors of every event in our world, from the exotic to the everyday.
Hi there, sports fans. This is Biff Burns.
And this is Steve Bosco.
And it's a beautiful day for baseball. Thanks to the weak nuclear force, the sun is busy releasing energy from the nuclei of atoms, making it a balmy 70 degrees here in Dodger Stadium.
The pitch is on the mound, and we're all set to get underway. He really got a piece of that one.
He sure did, Biff. But the Earth's gravitational force warped space so much it looks like an easy out.
Yep, he caught it all right.
Well, it's not so much that he caught it, it's more that the electromagnetic field set up by the atoms in his gloves surrounded the electromagnetic field of the ball.
Well, whatever you say.
Uh-huh.
Well, let's see. Who's up next? Looks like Reggie. At the batter's box, the pitcher is looking in to get his signal. What a wallet.
He just about knocked the quarks out of the ball.
It's out of here. It's a home run.
And this is Biff Burns saying until next time. This is Biff Burns saying so long.
And this is Steve Bosco rounding third and being thrown out at home.
The baseball and the bat are mostly empty space. Their solidity is an illusion created by the electromagnetic force field that binds their atoms together. Viewed on the subatomic level, a home run begins with the exchange of photons between atoms in the bat and atoms in the ball. The ball is repelled and flies away. We credit the home run to the batter, but the fundamental force responsible is electromagnetism. Infinite in range, it's electromagnetism that carries us light from the sun and stars. The weak nuclear force helps power the sun and presides over the phenomenon of nuclear decay. Tremendous amounts of energy are bound up in the nucleus of each atom. Some nuclei are unstable and can't contain their energy forever. When they decay, it's the weak force, carried by particles called weak bosons, that governs the process. The strong nuclear force binds quarks together to make protons and neutrons. Without it, there would be no atoms, and the universe would be a quark fog. The strong force is carried by particles that the physicists call gluons, because they act like the most perfect imaginable glue. Gravitation, the universal attraction of all massive particles toward one another, is the weakest of the four forces. But gravity has infinite range and it always attracts, never repels. This single-minded dedication makes gravity the force that holds the planets, the stars, and galaxies together. But why are there four forces, and why do they differ so profoundly in character? Einstein tried in vain to find an answer to that question. He sought what he called a simple and lucid image of the world, a single principle that would account for the baffling differences between the forces and the great variety of particles. What really interests me, he said, is whether God had any choice in the creation of the universe. He failed in that effort, but he never lost his faith that, as he put it, God is subtle but not malicious, that nature, though difficult to understand, ought at the root to be simple and beautiful.
Albert Einstein spent the last years of his life in this office at the Institute for Advanced Study in Princeton, New Jersey, working on the search for a unified theory of the forces of nature. He never found it, and the equations remained unfinished on the blackboard on the day he died. Today, the equations look a lot different, and they go by fancy names that Einstein never heard of, like supergravity and supersymmetry and superstring theory. But their goal is the same, to draw the disparate elements of physics together into one whole. Physics today is a patchwork. There are theories that account for each of the fundamental forces, and they do so marvelously well. They can predict the behavior of an electron spiraling away from an exploding galaxy, or the behavior of these photons arriving here from the sun. But they have little to say about why the forces of nature differ so curiously in character. Why, for instance, is there a positive and negative electrical charge, but no such thing, so far as we know, as negative gravity? Why do the strong and weak forces function only within the nucleus of the atom, when electromagnetism and gravitation are infinite in range?
The search for simplicity, the hope of identifying a fundamental force or a basic building block of matter, runs all through the history of physics since the days of the ancient Greeks. Atomic theory was already an old idea when Plato debated its merits with his pupil Aristotle. Aristotle proposed that there were two basic forces. He called them levity, the tendency of light objects to rise, and gravity, the tendency of heavy objects to fall. The Roman poet Lucretius popularized atomic theory.
Beautiful is the world created by the atoms. A wedding ring wears thin with the passage of years, yet we never see flecks of gold departing from the ring, for the gold is made of tiny atoms.
Amid the spiritualism of the Dark Ages, atomic theory, regarded as materialistic, was forgotten, only to be revived in the age of Isaac Newton, who saw the world as composed of atoms run by the force of gravity.
The universe is like a perfect machine. It is the force of gravity which holds the moon and planets in their orbits.
In the centuries that followed, experiments by Robert Boyle, John Dalton, and others revealed that, as Ernest Rutherford put it, the atom is a complex aggregate, not a simple entity. Rutherford found positively charged particles, protons, in the nucleus of the atom, and James Chadwick found neutrally charged neutrons there. Fresh light was shed on the concept of electrical charge when James Clerk Maxwell, in the first modern unified theory, showed that electricity is but an aspect of electromagnetic force. For a time it seemed that there might be just two fundamental forces, electromagnetism and gravitation. But then the force picture became more complex when Hideki Yukawa and Enrico Fermi and others identified two previously undetected forces acting within the nucleus, the strong and weak nuclear forces. With the 20th century came the identification not only of new forces, but of scores more particles. Einstein proved that energy itself is composed of particles, the quanta. Wolfgang Pauli found an odd particle called the neutrino, and the existence of the even stranger antimatter was established by Paul Dirac. The list kept growing. There were mesons and muons and pions. Said Fermi,
"If I could remember the names of all these particles, I would have been a botanist."
hopes of finding an ultimate building block of matter were raised anew when Murray Gell-Mann proposed that protons and neutrons are made of still smaller particles that he called quarks. And the concept of force was simplified as well when Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak force are aspects of a single electroweak force. Experiments by Simon van der Meer and Carlo Rubbia confirmed the electroweak theory. More ambitious, grand unified, and superunified theories followed, and by the mid-1980s, hopes ran high that physics might be within reach of an ultimate unified theory, a single equation able to explain the toilings of quarks and stars.
The trouble we're in now is that the standard model, the standard picture, is very elegant, it's very powerful, it explains so much, but it's not complete. It's incomplete, it has some flaws, and one of its greatest flaws is one which is hard to explain. It's an aesthetic flaw. It's too complicated. It has too many arbitrary parameters. We don't really see the creator twiddling 20 knobs to set 20 parameters to create the universe as we know it. That's too many. Ever since the Greeks started us on this road to understanding the atoms and the fundamental building blocks of the universe, we've had this prejudice that there's something simple underneath all of this. And 6 quarks and 6 leptons, and they're antiparticles, and they're coming in different colors and in different charges, is too complicated. And there's a deep feeling that the picture is not beautiful. And that drive for beauty, a simplicity and symmetry has been an unfailing guidepost to how to go in physics.
We haven't come to the bottom level yet. But as we approach it, we pick up intimations of an underlying beautiful theory, whose beauty we can only dimly see at the present time. We don't know that it's true. We don't know there really is a beautiful underlying theory. We don't know that as a species we're smart enough to learn what it is. But we do know that if we don't assume there is a beautiful underlying theory and assume that we're smart enough to learn what it is, we never will.
To my mind, there must be at the bottom of it all an utterly, not equation, not an utterly simple equation, but an utterly simple idea. And to me, that idea, when we finally discover it, will be so compelling, so inevitable, so beautiful, that we will all say to each other, "Oh, how could it have been otherwise?"
The unified theories suggest that nature would function more simply under conditions of extremely high energy. Take electromagnetism and the weak force. At normal energy levels, they seem very different. Electromagnetism is conveyed by photons. Photons are lightweight and they can travel for vast distances. But the weak force is a different matter. It's carried by weak bosons. They're heavy and can travel only very short distances before they exhaust themselves and decay. That's why the weak force is limited in range to the nucleus of the atom. But the theories say that the situation would change if we could turn up the heat. Fueled by the ambient energy, a new particle called the Z would appear and be capable of knitting together electromagnetism and the weak force. In this computer simulation, we'll watch as a Z particle decays and recombines to form a photon, carrier of electromagnetism. The photon, in turn, decays to form a pair of weak bosons, carriers of the weak force. And the bosons transform themselves back into a Z. What had been 2 forces is now 1 electroweak force. One way to test the theory was to look for Z particles.
Like salamanders, the mythological creatures that dwelt only in fire, the Z particles thrive only under conditions of intensely high energy. The universe today is too cold for Z particles to exist for long. They would find it chilly even in the interior of a supergiant star. When the electroweak theory first predicted that there ought to be such a thing as a Z particle, no laboratory on Earth could summon up enough heat to test that prediction. It wasn't until 1983 that science managed to fire up a spark hot enough to summon up the Z particle if it existed. It happened in a laboratory here on the borderline between Switzerland and France. The site was CERN, an international laboratory administered jointly by 13 European nations. Like other giant particle accelerators, CERN consumes as much electricity as a small city, but it manufactures nothing. The 6,000 people who work here are engaged in pure research. It all starts here. The particles that are accelerated are protons. They're easy to come by. There's at least one proton in the nucleus of every atom in the universe. And they're economical. This one bottle of hydrogen gas contains a full year's supply of protons for the CERN accelerator. The gas is emitted in infinitesimal little puffs through these computer-controlled valves and emerges into this pipe, the headwaters of the entire accelerator. Those tiny puffs of gas each contain as many protons as there are stars in the Milky Way galaxy. This steadfast old generator cranks out nearly 1,000,000 volts. The power is used to set up an electromagnetic field in this chamber. In the field, the negatively charged electrons orbiting the nucleus of each hydrogen atom are stripped away, leaving the denuded, positively charged proton. The electrons remain behind, and the protons speed off toward the main accelerator. For years, scientists had been accelerating protons in the giant CERN ring and colliding them with stationary targets. But now, for the first time, antiprotons, rare particles identical to protons but with opposite charge, were manufactured and stored in this antimatter collector. Then the antiprotons were injected into the main ring, hurtling in the opposite direction as the protons. When matter meets antimatter, the result is mutual annihilation. The impact between a single proton and antiproton releases, for a tiny fraction of a second, more energy than the electrical output of all the power plants in the world. Subatomic particles come reeling out of that tiny explosion and are captured in the onion skin layers of this giant particle detector. On the 28th of May, 1983, traces of a Z particle were detected in the debris emitted by a proton-antiproton collision. The electroweak unified theory had been confirmed. Carlo Rubbia of CERN shared the 1984 Nobel Prize in Physics for having conceived of the idea of colliding matter with antimatter.
What we are really doing here, we are making little banks. We are concentrating in a very small volume of space for a very short period of time enough energy, density, so that we can revive or replay, so to speak, on a very modest scale, what was really the state of affairs of the universe as a whole. The major progress in science has been made, I believe, by Galilei when he brought the experimental science to its right level of importance. And I still believe that, to a greater extent, our scientific progress is made through experimental science. It's not because I am an experimental scientist, just because I believe that there is always the final verdict, the final guidance, which comes from this physical phenomenon.
With electroweak theory a success, scientists went on to compose the so-called grand unified theories. These theories say that at still higher energy levels, 3 of the 4 forces might function as a single force. And here again, it's theorized that an exotic particle would do the work of unification. It's called the X particle. As we watch, a gluon, carrier of the strong force, strikes an X particle and is transformed into a photon, a carrier of electromagnetism. Alternately, a gluon striking an X can be transformed into a weak boson, carrier of the weak force. Particles of energy live on borrowed time. They gather themselves up from the stray energy in a vacuum, then ebb back into non-existence. The grand unified theories make the startling prediction that not just energy, but matter may be temporary. They say that protons, the particles that form the heart of every atom in the universe, are not permanent, as had been thought, but are destined to decay. The grand unified theories paint in deepened colors the old lesson that birth implies death. It's the latest chapter in a scientific saga that began here, in Venice, 375 years ago.
On August the 25th, 1609, Galileo led a procession of Venetian senators across the square and up to the top of that tower for their first look through his first telescope. Galileo was teaching just up the river at the University of Padua at the time. He was a respected teacher. Students flocked to his classes. He'd written a couple of good books. But his contract was about to expire. He'd never made enough money to get by, and he needed something to help his career. He found it. It was the telescope.
The senators were impressed. They granted Galileo tenure, gave him a promotion, and they commissioned telescopes for sighting ships at sea. But Galileo trained his telescopes on the sky. He saw that the moon has mountains as rugged as the Apennines, and that other planets have moons, and that the Milky Way runs deep with pasture lands of stars. And these sights helped to convince him that the heavens are as substantial and changeable as the earth.
Galileo's observations provided evidence that the stars and planets are worlds like ours, made of the same elements and functioning in accordance with the same physical laws. They drew together the realms of the large and small and married the earth to the universe.
The Venetians understood that nothing on earth lasts forever. They were citizens of a republic literally raised upon shifting sands and supported by the risky business of ocean-going trade. But they thought that the stars, at least, were immutable. Galileo's work changed that. By introducing into science the idea that the Earth is part of the universe, he set the stage for the subsequent discovery that even stars live and die. Since Galileo's day, telescopes have looked out into space to scales Galileo never dreamed of, and particle accelerators have looked just as far into the world of the small. And everywhere, they have found change. If the grand unified theories are right, not even atoms last forever. The city where Galileo glimpsed signs of the mortality of the heavens is itself in peril. Venice is sinking, its streets flooding with every winter's storm. The city cannot last forever, but it has company in that. Neither, it seems, can the sun, nor the stars, nor the atoms they're made of. Kamioka, Japan. Here in a lead mine, an experiment is underway to learn whether protons are mortal. To minimize interference by high-energy particles coming from space, the experiment is conducted nearly 2 miles underground. The unified theories predict that the average proton will last many billions of years. But by assembling an enormous quantity of protons, scientists can test the theories in the course of a year or two of careful observation. And that's what's being done here. A pit has been excavated, rigged with sensitive detectors, and then filled with 660 tons of pure water. If a proton in any one of the billions of water molecules in the tank were to decay, it would send out a telltale flash of light. Computers monitoring the flash of light would bring the news to waiting scientists. If the results are positive, the experiment will confirm an unsettling hypothesis that all the matter in the universe is a passing fancy, a stage in the ongoing dance of energy. If electromagnetism and the weak force unite at high energies, and the strong force joins with them at still higher energies, then might not all the four forces ultimately be one? Some of the most inventive minds in physics are at work trying to solve that riddle. Stephen Hawking ranks among the world's leading physicists, despite his having suffered for more than 20 years from a progressive disease of the central nervous system that's left him paralyzed and almost unable to speak. Hawking holds Isaac Newton's old chair as Lucasian Professor of Mathematics at Cambridge University. During a recent seminar at Caltech, his words were interpreted by a former student, supersymmetry physicist Nick Warner. Hawking's subject, the infancy of the universe.
Boundary conditions are the universe has no boundary. Sounds rather zen, doesn't it? What Stephen means by this is that space-time is some compact four-dimensional manifold. So, well, that's some. This is a general four manifold. Some. And label this some compact four manifold M with some metric on it, G mu nu, on the surface. And some, matter. And also some matter fields phi on the surface.
Do I understand then that you want the massive effective unification of a Yang-Mills or super Yang-Mills theory to be this low, like 10 to the 14? Or can that M be something else?
It may be something else.
But in any case, the M is a mass characteristic of whatever physics is responsible for the transition.
It is a mass. It generates. It generates the inflation cosmological constant. So. Stephen wants to just add that you can also explain the arrow of time from this. What do you think that would take? Much more time than we have. That's all.
No laboratory on Earth can produce the energy at which the four forces would act as one. Only the fires of Genesis were hot enough for that. The search for simplicity in the realm of the atom draws us out into the realm of the galaxies and back toward the beginning of time.
This program is brought to you by Texas Instruments, in the interest of better science education.
We live in a major spiral galaxy that we call the Milky Way. It's home to the Sun and a few 100 billion other stars. The galaxy belongs, in turn, to a cluster of galaxies. Astronomers call it the Local Group. And the Local Group is part of the Virgo supercluster, an archipelago of galaxies stretching across 100 million light-years of space. The galaxies are marching away from one another as the universe expands. In a computer simulation, based upon astronomical observations, we witness something never before seen by human eyes: the predicted scattering of the Virgo supercluster by the expansion of the universe over the course of the next 50 billion years. The expansion of the universe was predicted by Einstein's general theory of relativity, published in 1915. But the idea seemed so outlandish that Einstein himself rejected it. He introduced an extraneous term into the field equations to try to make his theoretical universe stand still. Later, Einstein would call this modification of the theory the worst blunder of my career. Then, in 1929, the American astronomer Edwin Hubble, without knowing of the relativity prediction, discovered that the universe is indeed expanding. Einstein and Hubble met in California in 1931 and celebrated Hubble's having found at the telescope what the mind of Einstein had conceived. Astronomer Alan Sandage, once Hubble's pupil, has devoted much of his career to studying the expansion of the universe.
It is not as if these galaxies are expanding into a space that's already there. The view is that the space itself is expanding, carrying the galaxies with it. The expansion creates the space. It's, well, the crucial analogy first made by Eddington as long ago as 1930, just 1 year after Hubble had announced the expansion, was you can conceptualize the thing as the two-dimensional analog by the surface of a balloon. You paint dots on the surface of a balloon and you blow it up. You put yourself on any dot, you seem to be the center and all the other dots move away from you. Now take the air out of the balloon and look what the dots do. All the dots come toward every other dot, and if you could take all of the air out of a perfect balloon, the surface itself would go to zero. All the dots would be back at one place at one time. Every place is the center of the expansion. When you talk about this, the question that always comes, well, can you find the center of the expansion? Every place is the center of the expansion. There is no center to the beginning. Everything was back at one place, and every place and every time was identical in the beginning.
Palomar Observatory in Southern California.
sitting inside a time machine of sorts, an instrument capable of looking directly into the past. Down at the bottom of the tube, far below me, there's a curved, polished mirror that can gather as much starlight as all the eyes in a community of 20,000 people. That light is brought here to a single intense focus, and through that tiny window, one can peer out for billions of light years in space and look back for billions of years into cosmic history. You can harvest some pretty old light with a telescope as large as the 200-inch reflector at Palomar. This image just coming in now is of a galaxy 40 million light years away. That means we're seeing it the way it looked 40 million years ago, which is a long time, but it's only a fraction of 1% of the time that's elapsed since the beginning of the expansion of the universe. If we were to plot our place in cosmic history, we might make a line representing time, starting with the Big Bang, the beginning of time as best we can understand it, and stretching down some 15 billion years or so to the present day. Here we are in a galaxy today, and we could have the vertical axis represent space. Now we can only see those events the light from which, traveling through space, has had time to reach us. And we can designate this by drawing what the scientists call a light cone. The angle of the sides of the cone is defined by the velocity of light, the fastest way we know of that information can travel. A galaxy like this, at 40 million light years away, is right here in our own neighborhood. And pretty much all the other galaxies that we can see clearly lie quite close by on the cosmological scheme of things. If we look further out, the galaxies begin to get pretty dim. Let's see if we can get a cluster of galaxies here. Each of those tiny little fuzzy dots, so small that you may find it difficult to see them, each of those dots is a sovereign galaxy of about 100 billion or so stars and untold numbers of planets. But the galaxies are so far away that existing telescopes, even the 200-inch at Palomar, can't make them out very clearly. The greatest distance to which we can see galaxies at the absolute maximum is half of the lifetime of the universe ago. Further than that, they're just too dim to be seen with existing telescopes. But fortunately, the early universe appears to have been inhabited by a class of objects called the quasars. The quasars, which may have been the nuclei of young galaxies going through a violent, youthful phase, are so bright, they shine so brilliantly, that we can see them at much greater distances than we can see galaxies. If we can call up an image of a quasar, this one is so far away that its light has been distorted by a galaxy lying between us and the quasar, and the result has been a double image. These two dots are actually of a single quasar, a quasar whose light has been traveling for so long that we see it as it was when the universe was less than 5 billion years old, back when the universe was less than 1/3 its present size and age. The quasars are so bright that thousands of them have been detected with telescopes here on Earth. And in fact, we could see them at even greater distances than we do if there were any. But at very great distances, getting back toward 15 billion years ago, the Palomar telescope and other large telescopes find no more quasars. The explanation seems to be that we're penetrating back to a time when the universe was so young that there hadn't yet been an opportunity for stars and galaxies and quasars to get organized out of the primordial material and to start shining. So way back here, at extremely long times ago, there's an epoch of darkness. And yet, even before that, it's possible to see another form of energy, the energy left over by the explosion that began the expansion of the universe, by the Big Bang itself. This energy permeates the universe, but it's been so thinned out by the cosmic expansion that it's shifted down from the wavelengths of visual light into the radio spectrum. And this cosmic background radiation, as it's called, can be detected using a sophisticated radio telescope, or, as chance would have it, by using an ordinary television set.
Any TV set hooked up to an antenna can detect the ancient photons from the cosmic background radiation. To see them, turn down the brightness control and tune the set to an empty channel, not right now, hopefully, but after the show, and about 1% of the specks of snow that you'll see on the screen are photons left over from the Big Bang itself. They're relics of the infancy of the universe, particles that have been hurtling through space since before the first stars and galaxies were born. The legacy of the Big Bang is still with us. The heat released by the sun and other stars represents a fraction of the energy stored in the nuclei of atoms at the outset of time. It was then, when the universe was still bathed in fire, that nature would have worked in the marvelously simple way glimpsed through the unified theories.
We've seen by looking at nature on the subatomic scale that the structures of matter and energy, and even the nature of the fundamental forces thought to govern their behavior throughout the universe, would have been simpler under conditions of extremely high energy. And we've seen by looking at nature on the large scale, out in the expanding universe of galaxies, that the universe began in just such a state of high energy. By putting these two lines of inquiry together, scientists have been able to trace the broad outlines of cosmic history from the first fraction of a second of the Big Bang down to the present day. We don't know all the details of this story by any means, of course. Parts of it are missing. Much of what's been surmised is doubtless distorted or simply wrong. But even at this early stage, it's possible to discern the grandeur and beauty and the extraordinary explanatory power of what is, after all, the ultimate history story, the history of the universe. The story of how a single kernel of energy could have become everything that there is. To examine the scientific account of Genesis and evolution in detail, suppose that the steps leading up the tower of this old lighthouse could carry us backward into cosmic history, so we could scrutinize every thread in the long tapestry of time. Let's imagine that each of the windows